Okay, hi everybody. Thanks for joining us for this session on massive and evolved stars at the Chandra Frontiers in Time Domain Science. This is our last session of the week, and we'll have a whole slate of sessions next week as well that I'll share with you at the end of the session. This session will feature 4 speakers, and our first speaker, if you want to start sharing your slides, is Jeno Sokoloski, coming from the Columbia University and LSST Corporation, and is going to talk to us about X-rays as tracers of shocks and burning in novae.
Are you seeing those slides, Rudy?
I am.
Great. So 10 years ago, the Fermi satellite detected transient gamma rays from a nova eruption. And this was not a normal nova. It was unusual in that instead of accreting, the white dwarf accreting from a main sequence star, it was accreting from a red giant, from the wind of a red giant, so that when the eruption happened, the ejecta actually plowed through the dense wind of the red giant and set up a system of shocks that are presumably what accelerated particles to relativistic speeds and allowed the gamma rays to be produced. So 2 years after this eruption, some authors, including me, wrote a paper on X-ray observations of this nova and confidently claimed that only novae that are erupting with a red giant companion will produce gamma rays. And since those are fairly rare, gamma rays will be rare from novae. So between 2012 and now, Fermi detected about 15 absolutely normal novae in gamma rays. So highlighting the danger of making a prediction based on a sample size of 1. Today, I'll tell you a bit about how this discovery of gamma rays from novae has overturned our picture of these very common eruptions. And I'll also go a bit into how Chandra is helping us develop a new picture of novae. Let's start with an oversimplified version. So what we have in a nova eruption, of course, is a white dwarf accreting from a companion star, and it is accreting until this hydrogen fuel builds up enough on the surface of the white dwarf that thermonuclear runaway ensues, and the ejecta, the envelope is expelled. And that is my cartoon on the left, shown in red. That's the ejecta. Now, after the thermonuclear runaway, actually burning continues in a quasi-steady state for typically a few weeks up to a few decades, and that continues to power the eruption. If you look to the right on my slide, there's a nice cartoon or schematic from a review by Mike Bode showing how at different wave bands, novae tend to brighten and then fade, sometimes just simply because the ejecta are expanding and then becoming diffuse and the photosphere is receding. But I'd like you to look a couple of features in the X-rays here. What's happening is on the right side, when the ejecta become diffuse enough that we can see down to the white dwarf, then we see X-rays from the shell burning white dwarf itself. And those are generally quite luminous, on the order of the Eddington luminosity for a white dwarf, which is around 10 to the 38 ergs per second. If you look at this curve, this little dip you might notice in the visual curve, that's because in some novae, dust is produced. And so you get a dust extinction event. So this is obviously a very simplified picture, and that's been known for a long time. People have seen in optical line profiles and in optical images that there's clumps, asphericities, and in some weak thermal X-ray emission, that the profile, the velocity distribution in that ejecta is not a monotonically decreasing function. Some of the ejecta are moving more quickly than earlier ejecta, and you get some collisions and weak shocks. Of course, the surprise that I mentioned in my opening is gamma rays. Gamma rays don't fit into that picture, that simplified picture at all. So here is a compilation of some gamma ray light curves from a very nice review that is about to come out, or maybe just came out, by Laura Chomick, Brian Metzger, and Ken Shen in annual reviews. And here, if you look the x-axis, what is being shown is a timescale of a bit over 40 days. The black points are gamma ray detections, and the gray points are upper limits. So you can see by a quick look here that the gamma ray detectable emission, and this is, by the way, GeV continuum emission. So this isn't MEV line emission from radioactive decays or something that's been predicted. This is continuum emission. Tends to last on the order of weeks, and it kind of bounces around a bit. So it's not a simple rise with the eruption and then fade. There's some wiggling around. It's useful to note that the majority of novae now that are nearby, by that I mean within a few, maybe 4 kiloparsecs or so, have been detected with Fermi. So, but not all. So there are some novae that are nearby and gamma ray faint. So this, I think, will eventually provide us with some clues about the origin of the gamma rays, but the majority are detected with Fermi if they're close enough. And these are detected with luminosities of about 10 to the 34 to 10 to the 36 Earths per second. And the flows in novae are non-relativistic. They range from hundreds to thousands of kilometers per second in speed. So how do you get gamma rays? You need some relativistic particles, and the most natural way to get those in such a system is with particle acceleration in shocks. So we're going to explore where those shocks might be, but no matter where they are, any shock that can produce gamma rays should also produce thermal X-ray emission. I'll be discussing that shortly. The two main scenarios that have been discussed in the literature about how to produce these gamma rays are one called the leptonic scenario, which is just another way of saying inverse Compton scattering, UV photons from the white dwarf itself, upscattering off of a distribution of relativistic electrons. The other possibility is the so-called hadronic scenario. And in that case, instead of electrons, you have relativistic protons that are colliding with non-relativistic protons and producing neutral pions, which then decay into gamma rays. In either of these scenarios, we expect non-thermal X-ray emission. In the leptonic scenario, you expect that to be stronger than in the hadronic scenario. Okay, so how has this discovery of gamma rays changed our picture of novae? The first breakthrough came, besides the recognition that there had to be powerful shocks, with the system called V959 MON, which was imaged in the radio and later with Hubble. And the cartoon on the right here, we'll see on the left, I'm telling you that the key change is going to be, we no longer think that novae are primarily spherical with some bumps and wiggles, but primarily aspherical and composed of two distinct flows. Again, it was known for a long time that novae produce equatorial rings and some bipolar outflows. The new appreciation is that this is the dominant mode of the ejection. Two distinct flows, one that's in the equatorial plane, and then a fast wind that collides with this dense, slow equatorial flow and gets shaped into a bipolar structure. This was imaged in the radio, and the important aspect there was that synchrotron knots were seen at the interface between those two flows, suggesting that the collision between them is what sets up the system of shocks that produces the gamma rays. Okay, so stepping back a little bit, what has Chandra revealed about novae? Chandra the satellite. I've included a picture of Chandrasekhar the person here as well to remind us about the Chandrasekhar limit, which of course is in the background in any discussion of novae, because one of the interesting aspects of novae is that they stand as the primary barrier for some high mass white dwarfs to accreting enough material to approach the Chandrasekhar limit and explode as a type 1a supernova. Okay, so has Chandra helped us understand what's happening in novae? First, we can divide that into three pieces, that question. First is by looking at the ejecta at early times. And then when those clear, the next stage is looking at the white dwarf itself. And then finally, at very late times, and in a few cases, the ejecta, when they expand years afterwards, if they're bright enough and the nova is near enough, we can see the structure of those ejecta, even resolving them with Chandra because of its high spatial resolution. So here's an example, called V959 Mon, and people have actually been doing work in this field for 2 decades. This is a recent example because it's one that I'm familiar with, but it builds on work done by many others with X-ray grating spectroscopy and understanding how to use those to extract valuable information about novae. So what we can learn from such spectra are, first of all, something about the abundances in the ejecta. They're known to be non-solar, of course, because what you're seeing is some CNO process material. And so that can be seen not only in the optical, but also in the X-rays. And for me, perhaps a little more equally interesting, I shouldn't say more, is you can, in some cases, learn about the composition of the white dwarf itself by whether or not neon is highly overabundant. So the white dwarf is either carbon-oxygen or oxygen-neon in composition, and the carbon-oxygen white dwarfs are those that can, in principle, gain enough material to explode as type 1As, or if they gain material, they can, in principle, explode as type 1As, whereas the oxygen-neon are thought that if they gain a lot of material, they will experience accretion-induced collapse. So here's an example of how the power of the gratings can reveal the underlying something that's the composition of the white dwarf, which is typically very difficult to assess. In addition to that, the line profiles can tell us about the dynamics of the outflow, and in particular, something that's relevant in this era of gamma rays from novae, the dynamics of the shocks themselves. So in systems where the ejecta might have very complex structures, the hot shocked plasma is particularly important for diagnosing the shocks, which are, of course, responsible for the gamma ray emission. So in this example, what the fitting of the Chandra spectra revealed is that there are 2 distinct plasmas, or 2 temperature plasma, and that those have distinct kinematic signatures. So I'll sort of jump to what I think is the punchline for this source, which is interesting, is that we are probably seeing the forward and reverse shocks as this fast wind plows through the dense torus. And one of these 2 shocks presumably was responsible for the gamma rays. Okay, so as I said, once the ejecta clear, we have a nice view down to the hot white dwarf itself. And there, if you look at the figure on the right-hand side top, is an example of a white dwarf atmosphere, a hot atmosphere of a burning shell on the surface of a white dwarf. And from fitting such an atmosphere model, we can get the effective temperature and connect that to the mass of the white dwarf, which is, again, another extremely important quantity for these systems, and one that can be challenging to determine. So the relationship, the reason there's a strong relationship between the effective temperature and the mass of the white dwarf, and that's been known theoretically and has recently, or I say has been confirmed empirically by various authors now looking at novae that are in the shell burning stage after the eruption. So for example, there's a nice review of this by Marina Orio and in a series of papers by led by Martin Henze. Okay, so there's the effective temperature that gives you the mass of the white dwarf. And in addition, some timing analysis. I believe these are from the low energy grading observations, but I'm not 100% sure. There is information available about the white dwarf, the hot white dwarf itself. So looking to the left on my slide is, I think, the first example of variability seen in this so-called super soft X-ray phase of after a nova. And this is in a paper by Jeremy Drake and collaborators of V1494 Aquila. And what's evident there is both some oscillations and a huge flare. So the oscillations, I think at least in this paper, they're not sure of the origin of that flare, but the oscillations seem to be non-radial pulsations of the white dwarf, kind of similar to what's seen in some hot central stars in planetary nebulae. On the bottom right, there's another example of oscillations detected by Chandra in a post-eruption hot burning white dwarf. And in that case, the authors there found some of the pulsations related to the spin of the white dwarf and others related to, again, non-radial pulsations of the white dwarf, opening up a new avenue for diagnosing that hot white dwarf. And finally, there is the case where very few cases where the novae are old enough and still bright enough in the X-rays that their remnants can be resolved. So on the left is a famous nova GK Per, which is more than 100 years since its big nova eruption. And in that case, the ejecta expanded into some dense interstellar medium. And as can be seen here, in this paper by Shulin Ballman, there was, you can see sort of a shock front there, and it produced both non-thermal and thermal X-rays. On the right is one of my favorite novae, RSOF, and here's some, I think the first, using some image reconstruction techniques and the resolving power of Chandra, Rudy Montes was able to, for the first time, see a bipolar X-ray outflow from a nova and how that flow evolves. Okay, but I told you that the shocks that produce gamma rays need to be very powerful. And what we had seen were only weak X-rays that don't seem to be consistent with what you'd expect from powerful shocks. So let's go over that. First of all, why do we know the shocks need to be powerful? Top line here, or the second line on my slide, we remember that the luminosity in the gamma rays is 10 to the 34 to 10 to the 36 ergs per second. But that represents only a very small fraction of the power in whatever shock is leading to the gamma ray production. And that's for two reasons. One, if you look in my top equation, what I've called epsilon non-thermal is the efficiency of accelerating particles to relativistic speeds. And that's thought to be around maybe 1% for shocks like those in novae. And then what I have as epsilon gamma is the fraction of those relativistic particles, or the energy in those relativistic particles that will actually come out as gamma rays. And that's also obviously less than 1 and possibly significantly less than 1. So if the detected gamma ray luminosity is, say, 10 to the 5 ergs per second, the shock power had to have been something like 10 to the 37 or 10 to the 38 ergs per second, which I want to point out is as luminous or as powerful as any other aspect of a nova. the burning shell, the optical luminosity, the bolometric luminosity, this is comparable. So it's clearly one of the, energetically speaking, one of the most important aspects of novae. But the lack of X-ray evidence for such powerful shocks is exactly why gamma rays were a surprise in the first place. So let's see if we can find those shocks. Because we expect them to be deeply buried in the ejecta, we started by looking with NuSTAR, where you can, even if the column, absorbing column is extremely high, we could still have a chance of seeing some X-ray emission. So far 3 novae have been observed in the X-rays with NuSTAR while they're still gamma ray bright. So in that first, say, 40 days from optical peak. One example is V5855 Sagittarius. And actually, I should just say for, I think all of these, the thermal plasma, optically thin thermal plasma was detected. In all cases, very highly absorbed, as you'd expect for a deeply buried shock. And at least, yeah, I think for all of them, the temperature of the shock is consistent with what you'd expect from the flows that, the flow speeds that we infer from the optical emission lines. So we know the flow speeds and what you, how fast the shock should be, and that directly corresponds to an X-ray temperature. And so it does seem like what we're seeing in the X-rays is the collision between flows that we can diagnose to some extent with optical spectroscopy. So, but there are some, so that makes sense. There are also some surprises as well. For one thing, no non-thermal X-ray emission has been detected. In this third source, I should say, it just erupted in July of this year. And this reference, by the way, the Sokoloski is a collaborator, but no relation to me. This is just an ATEL so far. So that one hasn't been, we haven't fully analyzed, but the other 2, there's no evidence for non-thermal X-rays. And also the X-ray emission, the thermal X-ray emission is very faint, even at the time when gamma rays are being produced. So we suspect there's a very powerful shock, but we're seeing very weak X-rays. So what does this tell us? First of all, the limits on non-thermal X-rays are fairly straightforward to interpret. They support the hadronic scenario for production of gamma rays, because we expect less, lower non-thermal X-rays from that scenario. The weak thermal X-rays, that's harder to understand. Could there be another shock that's even more deeply buried? For example, if we're seeing with NuSTAR only the forward shock, but not the reverse shock. Could the shock be non-radiative, which is counter to theory, the understanding of how you get the gamma rays? Or could the shock hot radiation from the hot plasma be reprocessed perhaps into the optical? So that is currently an active area of research. We don't know why the X-ray, the thermal X-ray emission from the shocks, even at the time of the gamma rays, is so faint. Okay, so let's bring Chandra in to this interesting question. And again, use an example that's very familiar with, D959 MON. What I'm showing on the left is on the x-axis, time in days since the outburst. So go to 140 days. The black points are swift fluxes. So the source was monitored with SWIFT. The blue line corresponds to when a Chandra observation was done, and the red line when a Suzaku observation was done. I'd like to argue that what helped us get information about this system was having all these facilities involved. So I already mentioned that the Chandra grading spectrum revealed that there were two plasmas, the one associated that we associate with the forward shock, one with the reverse shock. But which one with which plasma? Here's where the SWIFT monitoring comes in. From the reverse shock, we expect the temperature to remain fairly constant. So a little bit more similar to a standing shock, and the emission measure also to remain reasonably constant during some period initially. Whereas the forward shock is moving through a material with a decreasing density, we expect the velocity to evolve and the temperature to evolve. So what Swift revealed, it could only see one of the plasmas, and that one had a temperature and emission measure that were fairly constant. So we identified that as the reverse shock.
3 minutes.
Thank you. Then with Swift, we could also watch how the absorbing column evolved, telling us a bit about the material in front of the shocks. And yeah, okay, so here we have a plot, that same time scale of the column density evolving as a function of time. The red curve is what you would expect if the ejecta were ejected at T0 with the thermonuclear runaway, and that does not fit the data. Instead, what fits the data is an ejection that's delayed by about a month, in this case, 38 days. I think this is a very interesting finding that relates to the fundamental nature of how novae work and forces us to think a little bit about the role of these two flows that I mentioned, the slow toroidal flow and the fast wind, and what could be expelling the torus. In this particular system, we're looking through this, it's an edge-on system, so we're looking through the torus at the shocks. And if this result seems a bit strange, that in an eruption where you expect there's a thermonuclear runaway and everything is immediately expelled, it actually might be still semi-bound for about a month and then fully unbound. This system is not alone. There are two other novae as well, T-Pix and B906 CAR, that have similar evidence that suggests a similar delay in the full ejection of most of the mass in the system. So if we tie this back to our new picture of novae with a dense torus and then a fast wind blowing into that torus, it raises the question of, is it possible that that torus is initially produced by some process, for example, material spewing out the L2 point behind the donor star, it is only marginally bound initially, and then that second flow or some common envelope type process is needed to really eject the material from the system. All right, so our investigation of gamma rays and novae has led to a new picture and raised as many questions that it's answered. So what can the future hold, and in particular observations of these non-spherical cows? And this non-spherical cow here was created by my past grad student, Jennifer Weston. I will argue that to maximize scientific output and understand these systems, we'll need to think about a few things, like optimizing the timing of Chandra observations, obviously, since these are transient events, ensuring sufficient monitoring, for example, with Swift, both before and after X-ray grading observations to really allow us to get the information that we need, and perhaps enabling us, well, no, skip that, prioritize Chandra observations with multi-wavelength support, and perhaps even consider performing more observations on a smaller number of targets. What I have in mind is, for example, with the NOVA that I showed you, we were able to see both the forward and reverse shock, but that was actually 60 days after the gamma rays had stopped. If we can close that gap and maybe take some risks with more high signal to noise observations closer to when the gamma rays are being produced, we can connect the dots between new star observations and Chandra observations, tie it all together with Swift, and figure out where these powerful shocks are and what their nature is. So I'll just leave my conclusion slide up and maybe just focus on the last point, which is that Fermi surprised us with gamma rays from classical novae. And I think that Chandra can help us get to the physics behind that surprise, and that will have wide implications for other stellar transients which certainly will have shocks and produce gamma rays and accelerate particles in the era of time domain astrophysics. I can take questions.
Thank you, Jeno. If you have any questions for Jeno, please put them into the Q&A box. And I remind the participants that if you have or the panelists, if you have a question, feel free to raise your hand or enter it into the chat box since you don't have access to the Q&A box. If there are no questions from the attendees, or as I'm waiting for questions from the attendees, I'll ask you a question. Is there any information on the time scale for how long the Fermi gamma ray emission would last from the nova that have been detected?
Yeah, it looks like a typical time scale is weeks. But it does vary, but yeah,
And
I
then
think, weeks.
does it fade to non-detection, or
Mhm.
is it okay?
Yeah, but
So-
there are plenty of wiggles in there, and there's a nice there's a paper recently led by LSSTC in Nature Astronomy, where they see correlations between the gamma rays and optical emission that of these little bumps and wiggles that is suggesting that there is some reprocessing of the shock heated gas into the optical.
So the few that have not been detected,
Mhm.
is it possible that it's due to the time scale of the emission fading, or they were captured within a certain amount of time to see it?
I don't think so, because Fermi is scanning
Mhm.
all the time. I think it's more likely that some novae are clearly too far away, and there's some others that are nearby and have no gamma ray emission, where I think that the physics, they must not produce the same kind of shocks. So either if you have primarily an impulsively ejected white dwarf envelope, which we know sometimes happens when you have a very high mass white dwarf and a very thin envelope. So in recurrent novae, it could be everything gets expelled and then there's no opportunity to set up the slow torus and then have the wind collide with it. So you just have some different structure in the ejecta that might not lead to gamma ray production.
Great. So we have additional questions from our audience. Federico Ferchetti says, thanks for the fascinating talk. What non-thermal X-ray observations suggest for the magnetic field strength at the shocks? Or alternatively, what is the Alfvén Mach number? What could the Alfvén Mach number be? About multi-wavelength support, is there any radio counterpart to the gamma outburst?
Great questions. I think there were 3 in there. I'll try to answer what I can. So I'll say first off, I don't know about constraints on the Alfvén number that you request, that one in particular. The radio observations actually probably have the best hope of providing those constraints, because whereas we don't see non-thermal X-ray emission, we do see synchrotron radio emission in at least some cases. And so that can help us understand what the magnetic field strengths have to be. And the third one was about multi-wavelength support observations. Is that right?
Correct, for the gamma ray outburst.
Yeah. So, I'll try to not just say everything. We need everything, because of course that's the temptation. Radio is very important because we can resolve the ejecta and get a sense of both of the flow components. And like I said, synchrotron emission, optical, and also optical spectroscopy is huge, because you can really diagnose the flow speeds involved in the problem from the line profiles in the optical spectroscopy.
Great. And then we have another question here from Solon Ballman.
Oh, hi.
How many of these nova show high NH and X-rays, and how many and how many low? And the follow-up is, and does that correlate with the X-ray temperature, as in high T with low and high T with low NH?
Yeah. So you could imagine, I'm guessing you're thinking that a more deeply buried shock, would have a higher NH. If you're seeing different shocks, you could have different NH. I think that since the absorbing column evolves with time, it's probably the differences are more related to when a nova was observed. So the earlier you observe, the more likely you are to have an extremely high absorbing column, and then that decreases with time. But in terms of actually distinguishing between the different shocks, I think we're just at the beginning of that type of research. I'm not aware that we're able to identify the different absorbing columns in front of the different temperature shocks yet.
Great. And Solon says hi. And
Hi.
This question is from John Miller.
Uh-huh.
Is there a blueprint in the archive for the monitoring cadence that you would like to see in the future?
I'm going to guess that you're talking about Swift.
Let's see.
Yeah, and that's a good question. And unfortunately, it depends a bit on the nova, because for those who work on novae, there's a huge range of speed class. So in some cases, a lot of the exciting stuff happens very quickly, and you really only have a matter of weeks to get all the interesting information, at least from the perspective of watching the shock and the column evolve in front of the shock and looking at the ejecta. But others evolve more slowly. So unfortunately, I don't have a sense of what a good answer is. Like you saw with Nova Mon, we had Swift observations. I think we had like 15 over like every 10 days, maybe one. And that did do a very good job there.
Can our next speaker start preparing their slides? And I'll point out that Federico Solon had a comment for you that in GK per, the magnetic field strength was about milligauss range. And I will introduce our next speaker now. Our next speaker is Pragati Pradhan from MIT Kavli Institute for Astrophysics and Space Research. And she will talk to us about colliding winds of Wolf-Rayet 25 in high resolution X-rays. Please remember to share your slides and unmute. You're muted presently.
Sorry,
They...
I'm not able to see the second.
Oh, your slides might be displayed in full screen already, so you might have to stop that and then restart it. It's happened to me before.
Let me try that. No, I can't see my screen here. Okay. Oops. So is it possible that I just send the slides to you and then you can display it? Because I don't have an option to.
Yeah, you can. We can do that. Maria, do you have your slides ready to go? We could go Maria first.
Oh yes, I can do it now.
Okay, great. Sorry for the last minute.
Oh, no worries.
So our next speaker is actually Maria Georganti, and will talk to us about from the University of Southampton, and will talk to us about WZSEG, a magnetic propeller white dwarf system, ?
So hello everyone. First of all, I would like to thank you for giving me the opportunity to talk today here and communicate my research. So in this talk, I would like to give you a small overview of the project that I was working on the last year on WZ-SEG. But let me start with a small brief introduction on dwarf novae and accretive white dwarf systems. So dwarf novae are interacting binaries where the white dwarf accretes matter from its less massive companion. At the most common scenario, the companion star filters through slope and then transfers mass into the white dwarf through the inner Lagrangian point and the formation of an accretion disk. In general, these systems are transients. They alternate between long periods that they are in quiescence and they're quite faint to periods that the luminosity increases by several orders of magnitude, and the radiation dominates the whole electromagnetic spectrum. Today, the standard model that we have to explain these abrupt changes in luminosity and consequently the mass accretion rate is the disk instability model. This model states that the accretion disk will become unstable when the mass accretion rate coming from the component star will reach a critical value in the accretion disk. At that moment, the hydrogen in the disk will start to be ionized and the eruption will occur. The dwarf nova systems, though, display a wide range of phenomenology as far as the outburst light curves are concerned. So here you can see the visual light curve of one of the most popular dwarf nova out there, the one of ACIS, where you can see this steep rise and smooth decay as is interpreted by the disk instability model. Another example of this category is the case of V1504 Cygni, where you can see super outbursts occurring every few outbursts. But not all the systems, or not all the dwarf nova systems are interpreted based on the disk instability model. Of course, other models were introduced, like the tidal thermal instability or modification of the original disk instability model, or if we have to take into account if the outburst starts from the inner part of the disk and is propagating outwards or vice versa. In this project, the object that I'm working on is the WZ Sagitti. This object, here is the visual light curve of this object from its 2001 super outburst. As you can see, this light curve is not that similar with the previous ones. Here you can see a distinctive knee in the outburst decay, a dip, and subsequent reflaring. So what's so special about these features? And do we see these features in other objects as well? So these sharp deep decline features were linked like 2 years back by Campana in his paper that these sharp deep decline features is evident in other systems, in other magnetic rotating systems of different scales. Here you can see the case of Sachs J1808, which is an acritic millisecond pulsar. And as you can see here, we see this kind of behavior that we were looking for to explain in our object WZ Sagitti. Of course, in the case of the acritic millisecond pulsar, this kind of dimming was due to the magnetic propeller action. So we're trying to test our hypothesis that maybe in the case of WZ Sagitti, the magnetic propeller mechanism is responsible for this kind of structures. But before going into details about that, let me start introducing the system. WZ Sagitti is a spectacular system. To be more particular, it is located in a mere distance of 45 parsecs, so it's quite close to Earth. The two stellar components are orbiting each other with an orbital period of 82 minutes. And the two stars are identified. We know that we have a low mass ratio, we have a secondary brown dwarf orbiting a massive white dwarf with a spin period of 27.87 seconds. Apart from these unique attributes, though, this system displays super outbursts. Super outbursts so spectacular that they have a high amplitude of 8 Mach from the quiescent level, they are long in duration, and they are extremely rare. So we're trying to test our hypothesis if it's a magnetic propeller. So, but what's the basic picture that we have about magnetic propellers? So we know that if a star has a magnetic field rotating with an angular velocity of omega star, this magnetic field will interact with the surrounding ionized material of the disk, which are moving at Keplerian speeds. So in this case of magnetospheric accretion, we can establish 3 different regimes. The first one is where we have the spin equilibrium, so the two angular velocities are the same. The second configuration is that the accretion disk rotates faster than the white dwarf. So in this case, so the gas will continue to be accreted into the white dwarf surface following the magnetic field lines, as we see in this cartoon representation of the accretion column in our bottom right. And the third configuration that we can have is that the white dwarf rotates faster than the Kepler speed of the disk. In this case, we have creation of centrifugal barrier, so we have prevention of the material to be accreted inwards. So they are ejected away from the system, and only a small amount of this material will be impact the white dwarf. So having that in mind, knowing the theory, so we know that there is another magnetic propeller white dwarf system in existence. This one is the paradigm of the A-query. A-query is a unique system. The white dwarf is spinning around 33 seconds, which is comparable to the spin period we have for our system. The unique attribute that we are looking for here is the aperiodic flare activity on minute timescale that was presented, and it was reported by Ruggles and Horn back in 90s. Here you see the flare spectrum. So in the blue part of the spectrum, we have these emission lines, plethora of emission lines of high ionization species, and semi-forbidden lines, something that we do not see in dwarf novae spectra. The most prominent scenario for these flares is that we have a fragmented accretion flow from the companion star. So that means that we have diamagnetic blobs interacting with the magnetic field of the white dwarf. So material are expelled from the system, and only a small amount of this material will be accreted to the white dwarf, as I mentioned earlier. So this propeller signature is apparent in this variable component in this flare spectrum that we see here. So in our case, what we had was time-resolved high-resolution far UV spectroscopy in covering the outburst aftermath back in 2001. Here you can see the visual light curve again, where I highlighted the epochs that we have observations. The first one is in the plateau phase from a primary burst. The second one is in the dip, where we think that maybe would be a transition to a propeller state. And the third one is at the onset of the reflaring. So what we did first was to construct mean spectra for each of these phases. So we constructed the mean spectra for several time resolutions from 1 second to 5 minutes. Here, I show you the time resolution of 1 minute, as I believe that it's the most prominent, the resolution that we see more prominent our findings. So the plateau phase, in the plateau phase, we see mostly sub-features as well as weak emission structures. Here you can see the deep mean spectrum, again for 1 minute resolution, where we have mostly absorption features. So we may think that the white dwarf governs the UV emission. And here again, we have the eco-outburst phase. We have present both absorption features and weak emission structures, the first one. So we have interpreted as that disk may be present again around the white dwarf. But someone may wonder that maybe the mean spectra is not the appropriate tool in order to see this kind of variability, these propeller signatures, since the white dwarf may be dominate this radiation. So our next step was to construct RMS spectra. So RMS spectra is a powerful tool for the identification of spectral variability, since all the constant components are eliminated. So here we're trying to disentangle the constant component, which is the white dwarf emission, from a variable component, which is the propeller action. So here you can see the deep RMS spectrum. So to be more particular, so we have in the RMS spectrum divided by the Poisson scatter for 1 minute resolution. So it's evident that these lines displaying intrinsic variations, characteristic examples are the ones of silicon, range of silicon, and the carbon 4 doublet.
3 minutes.
Thank you, yes. But the most important part is the comparison between the RMS spectrum in the deep and the flare spectrum of the query, since it's what we're trying to compare. Comparing these spectra, we see that they're quite different. So to be more particular, in our object, these line features are not as broad as we see in a query. And of course, we have variations in different ionizing species and lack of semi-forbidden lines in our case. Second of all, we did the same for the eco-outburst phase. Again, we see variations in several lines, which is quite interesting of its own, but in terms of a magnetic propeller is not that significant. Again, we see lines that varying like sulfur, silicon, range of carbon. The most important here that I'd like to note is that comparing the RMS spectra both in the deep and the eco-outburst phase, we see that it's not that different. If we had the action of the magnetic propeller, we would expect that this RMS spectra would be different, as the first one is in the deep and the second one is at the onset of the reflaring. So in order to wrap up my talk, this peculiar behavior of these super outbursts is quite important for research, since it challenges the existent outburst models that we have, and maybe could implicate other acritic binaries like X-ray transients. And our current results we have indicate that there is no spectroscopic evidence of the existence of the magnetic propeller in our system. So that's all for me, and thank you for your attention.
Thank you. Sorry, I was muted. Thank you for that talk. It was really good, interesting stuff. If we have any questions from our audience, please include them in the Q&A box. And again, if our panelists have any questions, please ask them in the chat or raise your hand. I have a question. If you had any simultaneous HST and X-ray observations during the...
Yes, so back in 2001, we have, actually we have a multi-wavelength coverage, like we had some Chandra observations, but we haven't analyzed this yet.
Okay.
It's like our next step. We're trying first to find if we have some conclusions from the time-resolved UV spectroscopy from HST in order to see if we have propeller action. But it's quite important because actually we have observations from radio to X-rays. So it's quite nice to have all this information for the 2001 super outburst because they haven't been properly analyzed.
And you haven't, there's no teaser there that you can give us about what you've seen at all?
There were some like some small papers back for like this multi-wave coverage, but it was quite short. So I haven't tried to analyze all of this yet. So stay tuned for that.
Okay. So here's a question from Solenbaum, and just a comment and a question together. I wonder if you see any X-ray signatures and how does X-rays compare with AE Aquarius?
So basically until now, it's we're trying to compare UV, since it was that would be peculiar because in a query back in the days when they find this kind of flaring, they find this distinctive UV spectrum, which was quite different from regular non-magnetic CVs. So that we're trying to do in WZ tragedy, because if we compare these UV spectra and we would find some similarities, maybe that would be an indication of magnetic propeller also in our system. So I believe that since we have done the UV coverage, I believe we can actually go to X-rays or other wave bands.
Great. That's all the time that we have for questions now, but you do have some comments from
I can actually answer them like offline.
Yeah, and yeah, feel free to put your responses in the chat.
But yeah, for any comments, please, that's my mail. So if you want to talk about it, or for any comments for further, or some suggestions about the project, feel free to mail me or comment it on Zoom, and I can answer.
Great.
Thank you.
Okay, and for our next speaker, I'm actually going to share their slides as we've had some difficulty. Oops, that's not quite right. Sorry. Oh, sorry. Pardon me for the technical difficulties. Thank you for bearing with us. Okay, our next speaker is Pragati Pradhan from MIT, Kavli Institute for Astrophysics and Space Research, and will talk to us about colliding winds on WR25 in high-resolution X-rays.
Okay. Thank you so much, Rodolfo, and thank you, Maria, for covering for me. Sorry about this. It was working fine a few minutes back. Anyway, so I'm Pragati Pradhan. I'm currently a postdoc at MIT Kavli, working majorly with David Hidemader and Moritz Gunther. And today I'm going to be talking about colliding wind binary WR25. It is necessary here to mention that this work has been really a collaborative effort by everyone here, and David has been really involved in the project and very helpful, and it has been real fun working with the other collaborators as well, so a big shout out to all of them. Next slide, please. So this was supposed to be an animation. It's not working. That's fine. I'll just explain what colliding wind binaries are. Basically, it's a system of two massive stars, and they have very powerful winds, and they are in a binary system. Now, when they are rotating about the common center of mass, when they are close to each other, the winds of these two systems collide, and that results in a large shock front and causing high energy emission. And basically, this is the wind of, let's say, the larger star, the Wolf-Rayet star, and if this is the wind of a less massive star, the O star, and if you view it from the Earth this way, at different phases, you will be able to map the dynamics of the colliding wind binary based on what chalk front you are actually seeing. Next slide, please. So this is a simulation that was supposed to run. So this is the WR star, and this is O star. So basically, when it revolves around around the common center of mass, at some point it comes so close to the Wolf-Rayet star that the winds are seen to disrupt. And next slide, please. So what happens when this? So what happens when what happens to the shock heated plasma basically? So once the winds collide, the cooling parameter, which is chi here, this determines what regime the plasma falls in. So this chi is basically the cooling time, that is the time taken by the plasma to cool, divided by the flow time, that is the time taken by the plasma to flow out of the shock. And this, as you can see, is proportional to the velocity, the pre-shock velocity of the wind, the separation between the star and the shock, and the mass loss rate m dot. So when this chi is much greater than 1, then in this case we see that the cooling time is much longer. So the wind interaction zone mainly cools through what is called the adiabatic expansion. Now, in case of adiabatic expansion, the X-ray luminosity really follows a smooth 1 by r variation, where r is basically the distance between the two binary stars. Next, what happens is when chi is very much smaller than 1, then in this case the gas cools rapidly. So that is basically that happens because when the WR star is really revolving around the O star, the radiation from the O star, it tends to stop the wind of the WR star at some frequencies, at some distances, sorry, and that changes the velocity of the wind that is coming towards the O star. So when it slows down the velocity, this chi parameter changes as well. So in this case, in those regimes, we say that the gas is actually cooling under radiative regime, and in this case, the X-ray luminosity doesn't vary as smoothly as an adiabatic expansion, but what you would see is really a sharp, abrupt change in the X-ray luminosity. Now, another thing to really consider when we are talking about binaries with two unequal masses and therefore different wind momenta is the fact that they also undergo something called radiative braking, which is basically linked to the first one. Let's say if the wind from the Wolf-Rayet star has already reached an asymptotic velocity and has approached very close to the O star, it can stop even at asymptotic velocities, the O star can actually stop the WR wind, and that causes a really sharp change in the X-ray luminosity. So that basically is what is the radiative braking. So these are the regimes under which this shocked plasma fall under after collisions. Next slide, please. Mm. So how are these colliding wind binaries detected? So as you may have already guessed, X-ray luminosity is a major factor. As in the colliding wind binaries, they show greater X-ray luminosity compared to the individual stars put together, and the wind collision region is really the source for the hard X-rays that we additionally see. And even the pattern of the X-ray luminosity, there's a strong increase followed by a decline in the X-ray flux during a short period of time. There's an accompanying increase in the column density because, as you can imagine, after the winds collide, you have a lot of matter coming between the wind colliding region and the observer. And of course, the collision also leads to very hotter lines, for example, iron 25. Next slide, please.
Sorry for the delay. It might be my
No
internet.
problem.
Is it on the correct slide or no?
This is, we just need to advance one slide. Yeah, thank you. So I'm going to today talk about the colliding wind binary WR25. The whole point of showing this slide really is to highlight the work done by Arora et al. This is an extensive paper where the authors have fit in the X-ray spectrum for different X-ray spacecrafts. Like you have the Suzaku XIS, XRT, and the XMM Newton. Now, if you look into the lowermost panel here, that is the soft X-rays, which the authors claim as X-ray emission from individual stars. And the second last panel, which is the FH, I don't think you can see my pointer, but yeah, the FH here is basically the hard X-ray emission, which originates in the colliding in binary. As you can see, for FH at around just before periastron, this FH seems to increase just before 1. There's an increase in FH, and there's an increase in FH, and then that is really followed by a sharp increase in NH as well. So an increase in flux followed by an increase in the absorption column density is what we see for all the observations here, and that really is an important factor in determining. That is what we expect basically from a colliding wind binary such as WR25. Next slide, please. So let's talk about Chandra HETG observations here. So on the right, you can see a schematic here. That is the WN6 star. That is the more massive star. And then the two dots there around, which is around phase 0.944 are two observations corresponding to WI25. So this was a part of the HETG GTO observation. And that is what we have used to really determine the line diagnostics. Now, in addition to that, you see the gray dots on top of the plot as well. So they are the off-axis observations, which were really they happen to be in the field of view of Eta Carina, and therefore these observations have been. There are different observations, off-axis observations as well, from which we can use to determine the flux at these different phases. So you see the period of this is the period of this Wolf-Rayet WR25 is 208 days. The eccentricity is around 0.5. It has the masses of these two stars are pretty large. Especially, we should be really thinking about understanding WR stars in general, because they have really huge masses, and they are at the end stages of stellar evolution, which will ultimately evolve into black holes. So these are really interesting systems to also look into individually. Next slide, please. So this is the high energy spectrum for around periastron for WR25. As you can see, from around 1 angstrom, you see very hot emission lines of iron 25, which is basically what you would expect. You also see a lot of helium, strong helium-like lines. For example, you have the silicon 13 around 6.7. You have the magnesium around 9. So these are really different. So the spectrum is really rich and contains different emission lines. Now, typically, when you have such a high, such beautiful spectrum, what you do is really look into the plasma diagnostics that you can carry out with them. So, and that is what we have done. Next slide, please. So, what we have done is we have looked into the individual components of the helium-like lines. So as you know, the helium-like lines are they comprise of three. They are basically triplet states arising from 3 different transitions.
3 minutes, but sorry, yeah, it takes a while to refresh.
Yeah. So this is basically the R, I, and the F band. So you see that in this case, the when there is a UV excitation, for example, the excitation coming from the O star. So in that case, the F line is actually extinguished. So this ratio R equals to F by I can really be used to disentangle where exactly the lines are being produced, and that is what we have done. Next slide, please. I don't know if I'll finish this. I'll try. So this is the helium line diagnostics that we have carried out. So you see that this we have the R, I, and the F lines here. So the rightmost one is the F line. We are able to distinguish the. We are able to really diagnose the F lines as well, which indicate next slide, please, which indicates that the wind where the line region is really formed is really far away from the O star, because it has not been photoionized by the UV radiation from the wind. And also here, I'll take a minute to appreciate the width that you can see here. So the black dot is basically the width of the silicon line, and the red one here shows the line at the instrumental resolution. You see that the lines are really, next slide please, the lines are really broadened. So this is what we really find for other sources as well as, other lines as well. So when we determine the full width half maximum or the width for these lines, they seem to be pretty broad. And this is what we see on the left-hand side is the full width half maximum for this source. So the black dots here are Gaussian fits. The gray lines here are the piecewise plasma fits. And in order to show the difference between the full width half maximum from what you'd expect from single stars, I put this side by side, and you see that we don't really see a correlation between these. We don't see a correlation between the full width half maximum and the velocity and the wavelength as you would expect for single stars shown on the right. Next slide, please. So we also looked into the velocity components of these lines. And so this is the current observation on the right-hand side. As you can see, half of it, a part of the plasma is really moving towards us, while the part of the plasma is also receding. So between the receding and the approaching plasma, what we tend to see is more of the plasma which is actually being blue shifted. So on the left, as you can see, change in velocity is really negative. So that implies that what we are seeing is really the blue shifted line in this part of the observation. Next slide, please. So we also looked into the, so maybe you can move to the next slide also. So we also looked at the off-axis observations of this WR25. And in addition to the off-axis observation, as well as the Swift excited light curves, they don't really seem to show a 1/d dependence that I was talking earlier, implying probably radiative breaking is also more dominant in this kind of systems. Next slide, please. For WR25 in this case. And what we would really like to do next is to look into at different phases of the system. For example, here this is the on the right you can see this is the current observation that we have had. Next slide, please. So what we'd like to do is really look into the system at different angles. For example, what we can do is when we would look at this system at around phase 0.05 is when you really expect maybe redshift and less broadening and lower absorption as compared to, let's say, the phase on the right-hand side at 0.8, where you'll be seeing maybe mostly glow shifted lines with a large amount of absorption. So really this kind of observations at different phases will be necessary for us to understand. Next slide, please. Understand if the shock cone model that we are following for colliding wind binaries are really feasible, or if there is something else that needs to be explained. One really advantageous thing about W25 is that the orbital period of the system is, we can schedule both these observations within a year, and this is like different from other long period colliding with binaries, where you have orbital periods of the periods of years. But also the system is at high ecliptic latitude, so it's a challenge, but then the returns are really high. So I think this is what we would plan for next. And I end my talk here. Thank you.
Thank you so much. Apologize. It was changing
I'm sorry
immediately, but
about this.
then I think being host and running the YouTube stream and everything just stole all my bandwidth, and
I'm sorry, I don't know what happened.
that's okay. So do we have any questions from the audience? We may have a time for one before we move on to the next speaker. Maybe not.
I'm happy to take it offline.
Okay. I think we have a question, but I think it's for the previous speaker. Okay, well, then I will ask Joy to begin sharing her slides, and I will thank you very much. I'm sorry for the technical difficulty. Our next speaker is Joy Nichols, joining us from the Harvard Smithsonian Center for Astrophysics, and will speak to us about timing analysis with ACIS HETG spectra.
Can you see this all right?
Yes, I can.
Okay. I appreciate the opportunity to talk to you today about a timing analysis with ACIS HETG of the massive O-star Zeta Pup. This is a list of my collaborators here. Zeta Pup is the closest and brightest early O-star. It's believed to be a runaway and a fast rotator. It has several different photometric periods determined in the past at various wavelengths. It's known to have DAX in the UV, and no magnetic field has been detected. We acquired 813 kiloseconds of HETG data in 2018 and 2019 for this program. We also have nearly simultaneous data with the optical bright constellation of satellites. This is the cumulative spectrum using all 813 kiloseconds of data acquired for the program. The major emission lines have been identified here, and the fluxes shortward of 5 angstroms have been multiplied by a factor of 50 to highlight the emission lines that can be seen in that region. You can see the wealth of emission lines available in this very deep exposure of Zeta Pup. Light curves were created for the Chandra data count rate data using 4 kilosecond bins of the count rate data. The light curves were used as input to periodogram. We needed to correct those light curves for contamination because that was not part of our processing prior. We did find immediately that the X-ray data varied by 6% from peak to valley compared to 1.5% in the optical. This periodogram was created using a modified Fourier method, especially for data with time gaps. The red line is the 1% significant level. Using the broadband light curve, then, the most significant period is at 1.7820 days. This is a light period determined entirely from the X-ray data before comparison with optical data. We also had a very marginal detection of 5 to 6 days. Because of the large data gaps in Chandra data between observations, the periodogram is composed of a picket fence type of distribution, making period determination somewhat complicated. The light curves folded on the 1.78 day period for Chandra on the top and bright on the bottom are shown here. The large point in the Chandra light curve is the mean of all the 4 kilosecond time bins for all OBS IDs that fall in that phase bin. Since the coverage of the observations with Chandra was not uniform in phase space, the points had different numbers of 4 kilosecond bins, ranging from 5 to 21 per point. The bright points represent the mean of all orbits that are included in that phase bin. The coverage is quite uniform for bright, and they found a period of 1.7806 days, very close to the Chandra period that we found. Now, the maximum count rate for Chandra occurs at phase 0.8 to 0.1. It's very broad. The maximum count rate for the bright data occurs at phase 0.45, and these are on the same ephemeris. There's a secondary maximum in each data set. For Chandra, the secondary maximum is small, but it is a 2 sigma result after fitting a polynomial curve to the light curve and using the residuals. Next, we approach the question of variability in zeta pup in a different way. This time with fully calibrated spectral data, we sliced the data on with a time filter of 9 kiloseconds using TGCAP software. We then created a dynamic spectrum using these time slices arranged in phase space. And we checked the results with simulated data, basically a constant profile with Poisson noise applied. So here is the dynamic spectrum. We have wavelength on the x-axis and phase on the y-axis. And this is just the stack of 9 kilosecond time slices arranged in phase. You can see that the noise increases in the longward wavelength, and that's an expected result. The second strip is a residual. It is the mean, the residuals to the mean of the above image. So you can see, for example, regions that have lower flux than the mean are dark, and regions that have higher flux than the mean are brighter. And then the bottom one is a statistics image. It is the residuals divided by the uncertainty, which is based on the counts per bin. You can see here that there's a dark streak right down the middle at phase 0.4 to 0.6, indicating that not only the lines, but the continuum is varying with phase. This is a blow up of that dynamic image. I don't have any quantitative information on this spectrum, but you can see that there's a possible variation within a line over the course of a full phase. For example, magnesium 12, the line appears to have a centroid shift during the course of the phase. There's also indication of non-uniform profile parameters such as width and flux peak. This is an idealized diagram of a pair of co-rotating interaction regions, which I will call CIRs, C-I-Rs, evolving into a smooth stellar wind. The diagram is by Cranmer and Owocki in '96. For each CIR, the hotspot on the surface of the star generates the optical continuum. As the CIR moves away from the spot, optical emission lines are formed. The X-rays are formed further out in the arm of the CIR. The conditions in the wind can be very different from smooth in this part of the wind, and the information, the formation of the shocks will be affected. The shock formation depends on the existence of sufficient discontinuity in pressure, density, temperature, or velocity, which depends on the structure of the wind it encounters. These conditions might be met in a small or a large region for a particular CIR. The amount of X-ray emission we see also depends on our viewing angle, since the shocks can be somewhat extended. And finally, cold clouds and other occulting structures can be present in the wind that occult our view of these X-rays. So if we consider only the maximum peaks in the optical and the X-ray from the light curves, we find a time lag of about 0.4 in phase between the optical max and the X-ray max. That is, would suggest that the CIR is at least 9 stellar radii above the surface of the star, which is inconsistent with theory. However, if we consider the secondary peaks,
3 minutes, oh, sorry, 3 minutes remaining.
Oh, thank you. Where's my other peak? Okay, it's gone. If we look at the secondary peaks, the gap between the optical peak and the X-ray peak is only about 0.1 phase, which places the X-ray emission less than 3 stellar radii from the stellar surface. While it might seem counterintuitive to pair these primary and secondary peaks in this way, we know the strength of the X-ray emission depends very much on the environment it's evolving into and on any occultation. So if we assume that we have 2 CIRs on Zeta Pup's surface that are visible in the X-rays, we find that they're not exactly 0.5 phase apart. That would imply a non-solid rotation of the star or latitude migration of the spots, for example. So the conclusions are that Zeta Pup has a significant X-ray period of about 1.78 days. That's also seen in the contemporaneous bright optical data. The period is also seen in emission and lines and in continuum flux. We find the data are consistent with the detection of 2 separate CIRs from 2 separate hotspots on the stellar surface, with very different amounts of X-ray emission visible. But of course, this is only one possible interpretation of the data. That's it.
Thank you, Joy. That was really interesting. If you have any questions, remember to put them into the Q&A box if you have any questions for Joy. I'd like to ask a question about the analysis that you showed us. If you can go back to the the three panels of the stacked spectrum.
Please.
Further back, the one with the statistic.
I'm on my way back. Oh, gee.
Right there.
I don't
Yeah.
have the side panel. Okay, yeah.
So it almost seems like in the statistics, there's also something at about 0.2. Is that just a trick of the eye? It looks like it's dimming there, and it does look like it's present in the residuals, at least for the silicon
Dimming at what point?
at phase 0.2.
Yes, I agree. I see it.
Mm-hmm.
I see it.
Is that shown at anywhere else? Shown up
I
anywhere
didn't
else?
look. I didn't look. I'll go back and look what's happening at that point in the phase in the light curves.
Mm-hmm.
Because I didn't notice that.
It's a really interesting analysis that you've done here. It really shows a lot of interesting features.
It does. It gives you a really good view of the spectra, stacked up. You can look for things like, you'll see some bright spots in here, and you can line those up with iron lines, it turns out. So in the future, one could look into the iron lines and see what phase they're occurring at, if it's different from other things. It's just a hint,
Right. Okay, we have a question in the Q&A. This question is from Solon Bauman. They say, I could not catch on page 11, so slide 11, the Chandra and bright data seem almost completely out of phase. How do you interpret that?
Yes, that was our first surprise. Let's see if I get one here. Sorry. Here, this particular thing, yes. And immediately you see that the maximum of the optical is essentially the minimum of the X-rays and vice versa, which is where we came up with this phase lag of 0.45 up at this part. And that's just too much. It was an unexpected result. The idea of selecting different peaks that were only lagging by 0.1 is what seemed to make sense. But you have to accept the fact that the X-ray emission is virtually uncorrelated with the hotspot.
Great. If there's no further questions, we can open up. We have a few minutes. We can open up questions to everybody if anybody has a question for any of our speakers today. Joy, I would like to follow up Solon's question with it. You mentioned that these are contemporaneous observations, so there's no simultaneity in them, so you can't exactly go to that bright rise and look.
We do have simultaneous observations for several days. Several of these Chandra observations were simultaneous, but not all of them.
And have you tried to correlate those with each other to see if this 0.2 or 0.1 phase lag is present at the higher cadence?
Well, the trouble is that bright orbits are about 15 to 30 minutes. So it doesn't fit well into the Chandra time slots.
Right.
You get it's like peppers.
Right. Okay.
With Chandra, we have a bigger piece.
Right. Okay. Thank you very much, Joy. I'm going to take over the slide share now.
Because I can't figure out how to get rid of it. Oh, good.
I'd like to thank all of our speakers again for a really interesting session on massive and evolved stars, and the speakers from the earlier session as well. Um, I'd like to call out to you all that next week's schedule starts on Tuesday at 9 a.m. On ultraluminous X-ray sources, and then a session at 11 on gamma ray burst. And then Thursday, we have a full day of X-ray binaries starting at 8 a.m. here in the Eastern US and ending at 5:30 p.m. So it's a day of X-ray binaries. As a reminder, you can always view these videos on the YouTube channel, which you can find in your email. Thank you very much for joining us. I hope